Usually when we talk about a medical diagnosis, there is this expectation of precision. It feels like engineering almost.
Right, yeah, you want a really clear answer.
Exactly, like you break your arm and the x-ray shows that jagged white line in the bone
Mm.
and the doctor just points at it,
Mm.
broken or not broken. The universe gives you a perfectly clean, visible binary answer.
We really crave that kind of categorization, you
Yeah.
know? It is comforting to look at a system to isolate a problem and just know definitively what you were dealing with.
But the moment you step into the world of predicting the future, specifically the future of our entire planetary atmosphere, that clean X-ray machine just shatters.
It totally shatters, yeah.
We are looking at a predictive landscape that is inherently murky. I mean,
Right.
you are dealing with a fluid envelope swirling around a spinning rock that is heated unevenly by a star and is full of moisture that is constantly changing states.
It is the absolute definition of diagnostic muddy waters. You have this
Yeah.
chaotic, nonlinear system where a microscopic change in temperature over the Pacific can literally dictate whether a blizzard hits New York a week later.
Which is wild to think about.
It is. And yet somehow we have managed to build a machine that can look into those muddy waters and tell you with astonishing accuracy when a storm is going to hit your hometown 5 days from now.
That magic is exactly what we are unpacking today for you on this deep dive. We are tracing an epic scientific journey. We are going to look at how a single scientist working with punch cards and these massive, clunky 1960s mainframes essentially turned the sky into math.
And won a Nobel Prize for it.
Yes, won a Nobel Prize and laid the foundation for a modern forecasting system that, according to our sources, is now facing an unprecedented existential threat.
Because when you look at your phone and see that it's going to rain at 4:00 p.m. on Thursday, it feels like an automated convenience, right? Like an app just knows.
Totally.
But today's source dossier shows us that this capability is actually the result of rigorous, grueling, decades-long human obsession.
And to guide us through this, our stack of sources is incredibly diverse. We have historical timelines of meteorology. We have the actual scientific retrospectives.
Like the landmark 1967 paper.
Yes, exactly. That paper that changed atmospheric physics forever, plus a 1963 paper on chaos theory that proved why predicting the weather is the hardest mathematical problem on Earth.
And pulling us right up to the present day, we are looking at contemporary government budget proposals that could dismantle the very laboratories where all of this started.
The narrative arc here is stark. We're looking at the rise of a capability that society takes entirely for granted, contrasted with the reality of how fragile that scientific infrastructure actually is. So, okay, let's unpack this and pull you back to 1958.
Washington, D.C.
Right. A young scientist named Syukuro Manabe, known to his colleagues as Suki, has just emigrated from Japan.
He was recruited by Joseph Smigorinsky to join the U.S. Weather Bureau's General Circulation Research Laboratory.
And to really understand what Manabe was stepping into, we have to talk about what meteorology looked like in the late 1950s. Because it was not a hard physical science.
Not at all. It was essentially an empirical craft.
If you walked into a weather bureau back then, you would see people hunched over massive paper synoptic maps.
Forecasters would look at the current temperature and pressure readings, and then they would dig through literal physical filing cabinets of historical archives.
Just searching for a match.
Exactly. They were looking for a day in the past that roughly matched the current map.
So if the map on a Tuesday in 1958 looked somewhat similar to a map from a Thursday in 1942, and it rained the following day in 1942, they would just predict rain for tomorrow.
Which is wild, right?
Right.
They were forecasting by looking in the rearview mirror. Pattern matching.
Which has severe limitations because the atmosphere never actually repeats itself perfectly.
Right, the variables are just too immense. But Manabe and his team at this laboratory had a completely radical idea. They wanted to abandon the historical maps entirely.
They wanted to build a three-dimensional atmosphere inside a digital computer.
Using the fundamental laws of fluid dynamics and thermodynamics to generate the future from scratch.
Which, to the practical forecasters of the time, sounded like an expensive academic fantasy. I mean, the computers of the late 1950s and early 60s were less powerful than the smart microwave sitting in your kitchen right now.
Oh yeah, we are talking about machines with a few kilobytes of memory.
And Manabe's first job wasn't to simulate the whole planet. He was given a very specific, unglamorous assignment.
Develop a radiative transfer module.
He had to solve the mathematics of sunlight.
Because the entire climate system is driven by solar radiation, Manabe had to figure out how to mathematically represent shortwave solar radiation entering the Earth's atmosphere.
How it interacts with different gases.
Exactly.
Oh.
And then how long-wave infrared radiation, which we feel as heat, escapes back out into space.
So let's break down the actual physics of what he was trying to code here. When sunlight hits the Earth, it warms the ground. The ground then radiates that heat back upwards as infrared energy.
But our atmosphere isn't just empty space, right? It's full of gases like nitrogen, oxygen, water vapor, and carbon dioxide.
So Manabe had to encode decades of complex spectroscopy.
Which is the study of how light and matter interact.
Right. He had to put all of that into equations a mainframe could process.
He was figuring out the absorption spectrums of specific molecules. A molecule of carbon dioxide, for example, is completely transparent to shortwave sunlight coming in.
But it absorbs and re-emits the long-wave infrared heat trying to escape.
Exactly.
So for you listening, imagine trying to balance a microscopic checkbook for the entire sky.
That is a great way to put it.
You are accounting for every single penny of sunlight coming in and every single penny of heat bouncing out cell by mathematical cell.
On a machine that barely had any processing power, getting the computer to run these equations was an absolute ordeal. You couldn't just hit enter.
No, you had to translate your equations onto physical punch cards.
Carry those heavy boxes of cards to a technician's schedule machine time weeks in advance and pray you didn't have a single typo.
Because one misplaced decimal, the program crashes, and you wait another 3 weeks to try again.
But Manabe's patience was legendary. He actually managed to build this radiative transfer module, essentially creating the mathematical accounting for how sunlight heats a planet.
And that checkbook, that module, became the engine for a breakthrough that would fundamentally change climate science forever.
Because once you have a working mathematical model of how radiation interacts with gases, you can run experiments that are physically impossible in the real world.
Which brings us to 1967. Manabe, working with his colleague Richard Weatherald, publishes this landmark paper.
They take this massive swirling atmosphere, but instead of modeling a 3D Earth, they strip away all the complexity.
They model a single one-dimensional vertical column of air, just a straight mathematical line from the surface of the Earth up to the top of the atmosphere.
And inside that one invisible tube, they ask a simple question. What happens if we double the amount of carbon dioxide?
The elegance of that simplification is profound.
It really is.
Though I have to play devil's advocate here and push back on that a bit, because stripping away the complexity seems like a massive flaw.
How so?
Well, if you reduce the massive chaotic sky to a single vertical column, you are eliminating ocean currents. You are eliminating wind. You are eliminating the horizontal movement of clouds.
True.
It feels like trying to understand the complexity of the ocean by staring at a single glass of salt water. How does a one-dimensional column prove anything about the actual whole planet?
Your skepticism is exactly what many scientists felt at the time, actually. But this is the power of working from first principles.
Okay.
If you want to know exactly what carbon dioxide does to temperature, you absolutely must remove all those other chaotic variables.
So they were just noise getting in the way.
Exactly. If you leave the wind and the ocean currents in the model, their natural variability will mask the pure physical effect of the CO2. Manabe isolated the fundamental physics of the greenhouse effect mathematically.
So by stripping away the noise, he created a pure physical laboratory environment inside the computer.
And the numbers that mainframe spat out are honestly chilling. When he doubled the CO2 in that column, the model produced roughly 2.4 degrees Celsius of warming at the surface.
A number that remains incredibly consistent with the most advanced supercomputer models we run today.
Yes, perfectly in line. But the total warming wasn't even the most important part of the 1967 paper. The crucial insight was where the warming occurred within that vertical column.
Right. The model showed that the lower atmosphere, the troposphere, warmed up, but the upper atmosphere, the stratosphere, actually cooled down.
And let's explain why that happens, because this is the smoking gun of climate science.
If the sun were just burning hotter and warming the Earth naturally, the entire column of air from the ground to the edge of space would warm up evenly.
But if greenhouse gases are acting like a blanket trapping heat near the surface, less of that heat radiates upward into the stratosphere.
So the lower atmosphere gets hotter and the upper atmosphere is starved of heat and cools. Manabe's model predicted that exact thermodynamic fingerprint in 1967.
It was a falsifiable physical prediction. He isolated the human carbon emission variable mathematically.
And to fully appreciate how this theoretical math was eventually proven in the real world, our sources point us to a German oceanographer named Klaus Hasselmann,
who eventually shared the 2021 Nobel Prize with Manabe.
Hasselmann comes into the picture in the 1970s because Manabe proved the fundamental physics of why carbon dioxide causes warming in a controlled, sterile model. But the real world is messy.
Very messy. The Earth's temperature naturally fluctuates due to volcanoes, solar cycles, and El Niño events.
So Hasselman had to figure out how to find Manabe's 2.4-degree signal hidden inside all that natural noise.
And he approached the climate like a physicist studying Brownian motion, the random erratic movement of particles. He developed stochastic climate models.
Stochastic referring to systems with random probability distributions.
Right. Hasselman figured out how to mathematically model the random, chaotic day-to-day weather as background noise, allowing scientists to actually filter it out.
He essentially built a highly advanced mathematical sieve. You pour decades of messy, chaotic temperature readings through Hasselman's stochastic filter, the natural noise drains away, and what gets caught in the mesh is that exact, undeniable fingerprint Manabe predicted.
A warming troposphere and a cooling stratosphere. Manabe built the physical proof in the lab, and Hasselman built the mathematical net to catch it happening in the wild.
Together, they formed the absolute bedrock of modern climate attribution.
But staying with Manabe, that 1D column was just the beginning. By 1968, his laboratory had relocated to Princeton University and was renamed the Geophysical Fluid Dynamics Laboratory, or GFDL.
And throughout the 1970s, Manabe's team took that single column of air and multiplied it. They wrapped the Earth in a grid of these columns.
They built the first three-dimensional general circulation models. They assigned complex equations of motion and thermodynamics to every single cell in that global grid.
And then they did something even more ambitious. They coupled the atmospheric model to an ocean model.
Which is incredibly hard.
They created a digital Earth where the sky and the sea could mathematically exchange heat and moisture.
Manabe basically built the perfect physics engine.
But any engine, no matter how perfectly engineered, is utterly useless without fuel. In the world of weather forecasting, the fuel that makes those equations run is data.
It is the current state of the weather.
You have to know precisely what the temperature, pressure, and humidity are right now, plug those initial conditions into the model, and let the physics calculate tomorrow.
But right around the time Manabe is building this engine, a mathematician at MIT proves exactly why gathering that initial data is going to be the hardest challenge in the history of science.
Enter Edward Lorenz.
Mm-hmm.
In 1963, Lorenz publishes a paper titled Deterministic Non-Periodic Flow.
And he inadvertently discovers a mathematical law that serves as the ultimate villain to anyone trying to predict the future.
His discovery happens completely by accident, and it comes down to a simple rounding error.
He was running a primitive weather simulation on a Royal McBee computer. He wanted to re-examine a specific sequence, so to save time, he started the run from the middle instead of the beginning.
He typed in the initial conditions by just reading the numbers off a previous paper printout.
But the computer's internal memory calculated the numbers to 6 decimal places, something like 0.506127.
But the printer, just to save ink and space on the page, only printed 3 decimal places, 0.506.
So Lorenz enters 0.506. He lops off an incredibly microscopic fraction.
A difference so small it's the atmospheric equivalent of a millimeter. He goes to get a cup of coffee, and when he comes back, the new simulation hasn't just diverged slightly from the original run.
After a few simulated weeks, the weather in the computer bears absolutely no resemblance to the previous run.
It is a completely different atmospheric reality just from missing a thousandth of a decimal point.
This phenomenon is what Lorenz would later introduce to the public in a famous 1972 lecture as the butterfly effect.
The concept that a butterfly flapping its wings in Brazil could create a microscopic disturbance that eventually cascades through the atmosphere to cause a tornado in Texas.
He proved that the atmosphere is a deterministic, chaotic system.
Let's unpack that term. Deterministic, meaning it follows strict physical laws. Gravity thermodynamics, fluid dynamics, these aren't random. Manabe's equations work perfectly.
But chaotic means the system is hypersensitive to its initial conditions.
Here is where it gets really interesting. To put this in an everyday analogy, imagine you are playing billiards. You are setting up the break.
Okay, I can picture that.
If you calculate the angle and force of your cue stick perfectly, physics dictates you can predict exactly where every ball will go.
Right. It's just math at that point.
But if your measurement of your cue stick's angle is wrong by literally a fraction of a millimeter, the cue ball strikes the rack slightly off center. The energy disperses differently. The balls collide differently.
And within 3 seconds, the entire table looks completely different than your prediction.
Exactly. Lorenz basically proved the Earth's atmosphere is an infinitely complex billiards table. And those microscopic errors don't just sit there. They multiply and amplify through the equations until your forecast is useless.
Lorenz established a theoretical mathematical ceiling on weather prediction. He calculated that because human beings can never measure the entire globe down to the millimeter, deterministic weather forecasting has a hard limit.
After about 2 weeks, those microscopic observation errors will always grow large enough to overwhelm the physics.
So a perfect day-by-day forecast beyond 2 weeks is mathematically impossible.
So Lorenz proves that to fight chaos, you need data that is impossibly precise. High-quality observation data isn't just something meteorologists want so they feel confident.
It is a strict mathematical requirement.
If you don't feed Manabe's engine, a near-perfect mirror of reality to start from chaos wins immediately. But the Earth is mostly uninhabitable ocean and empty atmosphere. How do you measure a void?
You have to build an unprecedented global physical network. The scientists at the National Oceanic and Atmospheric Administration, NOAA, couldn't just sit in laboratories writing code.
They had to go out into the real world and build an arsenal designed purely to gather those initial conditions and fight Lorenz's chaos.
And we really should spend some time marveling at the human scale of the infrastructure they actually built, because these aren't textbook abstractions.
No, the scale is staggering. Let's start with the oldest tool, which sounds incredibly low-tech but remains absolutely vital today: the radiosonde, the weather balloon.
The U.S. Weather Bureau started this network back in 1937, actually.
Every single day, twice a day, from 900 stations around the world, about 100 of them just in the U.S., people walk outside and launch a massive balloon filled with hydrogen or helium.
Carrying a small package of highly calibrated instruments.
And these balloons ascend to over 115,000 feet. They go straight into the stratosphere to the very edge of space where the sky literally turns black.
And as they climb, these sensors are constantly transmitting temperature, pressure, and humidity data back to the ground.
They also use GPS to track exactly how the balloon drifts, which calculates the exact wind speed and direction at every single altitude layer. Now, you might wonder why we still launch physical balloons when we have billions of dollars of highly advanced satellites in orbit.
Right. Why bother with balloons?
Well, satellites are brilliant at scanning the horizontal top of the cloud deck, and their infrared sensors can measure the surface temperature of the ocean beautifully.
But infrared and microwave sounders on satellites really struggle to see inside the atmospheric column with high vertical resolution.
A satellite has a very hard time telling you the precise difference in temperature and wind shear between 10,000 feet and 10,500 feet.
And radiosondes provide that exact vertical spine of data. When a balloon launch fails, especially in remote areas, the supercomputer models objectively degrade.
Because chaos creeps in, because the vertical profile is missing.
So we have balloons touching the edge of space to profile the air, but what about the ocean?
All right, because Manabe proved you have to couple the atmosphere to the ocean. The ocean is this massive thermal battery storing heat and dictating the weather above it.
But how do you measure the temperature deep underwater in the middle of the Pacific Ocean?
You learn the hard way, and then you build a massive grid in the water. The Tiotriton Array is the perfect example of this.
In 1982 and 1983, a massive El Niño event occurred.
And for context, an El Niño occurs when the trade winds weaken, and a massive pool of incredibly warm water sloshes eastward across the equatorial Pacific towards South America.
It drastically alters global weather patterns. The 1982 event destroyed the anchovy fisheries in Peru, caused devastating floods in California, and triggered severe droughts in Australia.
It caused an estimated $13 billion in global damages.
And the scientific community was almost entirely blindsided by it.
Because the precursor signals for an El Niño live deep underwater along the thermocline, weeks or months before that warm water actually surfaces and interacts with the atmosphere.
And you cannot see those deep thermal waves from a satellite.
So after the 1982 disaster, NOAA's Pacific Marine Environmental Laboratory decided they could never be caught blind again. They spent the next decade deploying an array of 70 moored buoys straight across the deep equatorial Pacific.
Think about the logistical nightmare of that engineering project. Can you imagine keeping a grid of buoys functional in the middle of the Pacific Ocean just to catch a 6-month warning on El Niño?
It is insane. You are anchoring heavy, highly sensitive electronic buoys to the ocean floor, sometimes 3 miles deep.
You have to keep this massive grid functional in the most corrosive, violent environment on Earth. They are constantly dealing with barnacle growth, fouling the sensors, massive ocean storms, and even fishing ships accidentally striking them.
All of this effort just to measure the deep water temperature. But the investment worked perfectly.
It really did. By the time the massive 1997 El Niño began forming deep underwater, The TAO array detected the thermal shift 6 months in advance.
The supercomputer models, finally fed with accurate deep ocean data, predicted the event beautifully. Governments and agricultural sectors had months to prepare shifting supply chains and water management strategies.
So the buoys and balloons handle the baseline global data. But what happens when the chaos organizes into a monster?
What happens when a hurricane is bearing down on a populated coast? You can't just wait for a buoy to happen to be in the storm's path.
No, you have to go to the storm. You have to fly an aircraft directly into it.
The hurricane hunters. The sheer audacity of this program is incredible. We are talking about two heavily modified Lockheed WP-3D Orion turboprops nicknamed Kermit and Miss Piggy.
These planes were acquired straight from the Lockheed production line in the mid-1970s, and they remain the only civilian hurricane reconnaissance fleet equipped with lower fuselage and tail Doppler radar.
Consider the aerodynamics and the sheer physical punishment involved here. You are flying a 4-engine turboprop aircraft directly into the eye wall of a Category 5 hurricane.
You are intentionally navigating through extreme updrafts and downdrafts, the most violent turbulence on the planet.
And the main reason they are in there is to deploy something called a drop wind sonde.
Which is essentially a weather balloon in reverse.
Exactly. They drop a cardboard tube packed with sensors out of the bottom of the plane. It deploys a tiny parachute and falls down to the ocean surface, tumbling right through the most violent part of the eye wall and into the boundary layer.
That's the lowest part of the atmosphere where the storm physically draws its energy from the ocean heat.
And satellites cannot see the exact wind speed underneath the heavy rain bands of a hurricane. If you don't fly the plane into the storm and drop that instrument, the models are mathematically flying blind.
As the drop wind zone falls, it uses GPS to calculate wind shear precisely. A single flight from Kermit or Miss Piggy can find that a storm's core winds are 20 knots faster than the satellite estimates.
That precise data point shifts the entire forecast, which is literally the difference between an emergency manager telling a coastal city to shelter in place or ordering a mandatory evacuation immediately. The precision is life and death.
And speaking of the razor's edge of life and death forecasting, there is one more vital piece of infrastructure we need to examine.
1,000 miles away from the ocean in Norman, Oklahoma, there is a laboratory dedicated to the hardest, fastest forecasting problem in meteorology, the tornado.
The National Severe Storms Laboratory, NSSL, because a hurricane gives you days to prepare, but a tornado gives you minutes.
In 1964, engineers at the NSSL took an existing weather radar and made a critical engineering modification. They enabled it to transmit in pulses, creating the first operational pulsed Doppler weather radar.
Standard radar is relatively simple. It sends out a radio wave, it bounces off a raindrop, and it comes back. That tells you where the rain is and how heavy it is. It gives you reflectivity.
But Doppler radar does something much more advanced. It looks at the shift in the frequency of the returning signal. It's the exact same physics as an ambulance siren.
Right when the ambulance is driving toward you, the sound waves compress and the pitch goes up.
And when it drives away, the waves stretch out and the pitch goes down. Doppler radar looks at that shift to calculate whether those raindrops are moving toward the radar dish or away from it.
Which means the radar is no longer just seeing rain, it is seeing wind velocity. It can see rotation inside the cloud.
The ultimate proof of this concept came on May 24, 1973. A massive F4 tornado struck Union City, Oklahoma.
NSSL researchers, using their experimental Doppler radar, observed the storm's entire life cycle.
They captured a specific tight rotation signature in the mid-levels of the thunderstorm minutes before the funnel ever touched the ground.
They discovered the tornadic vortex signature, the TVS.
Once meteorologists knew exactly what that signature looked like on a velocity radar screen, it changed everything. It became the design standard for the NEXRAD WSR-88D network, the massive infrastructure of 159 radar domes that were installed across the United States in the 1990s.
Because of that specific research in Oklahoma, tornado warnings went from practically zero, literally waiting for someone to see a funnel cloud and call it in, to an average of 13 minutes of lead time today.
When you zoom out and look at all of this, Manabe's millions of lines of Fortran code running on supercomputers, the balloons touching the edge of space, the heavy buoys anchored in the deep Pacific, the turboprops flying into eye walls, and the Doppler domes scanning for rotation, you realize they built a planetary-scale sensory nervous system.
It is a massive, sprawling machine designed for one purpose: to gather the initial conditions required to defeat Lorenz's chaos.
And we have to talk about the economic masterpiece that this machine has produced, because we all complain when a forecaster gets the weekend rain wrong. but we completely fail to grasp how incredibly accurate the system has become.
The statistics in the source dossier are staggering, honestly.
Let's look at the 5-day forecast. In the 1980s, a 3-day forecast was about as accurate as a 1-day forecast is today. A 5-day forecast in the 80s was barely better than just guessing based on historical averages.
But today, a 5-day forecast is as accurate as a 2-day forecast was in the 1980s.
They have essentially pushed back the horizon of the unknown future by 3 full days.
And with hurricanes, the improvement is even more mathematically striking. Since the 1990s, the National Hurricane Center has cut the average 5-day track error in half.
They shrank the cone of uncertainty by 50%, and the financial impact of that is massive.
Because when a hurricane is approaching, emergency managers have to order evacuations.
It costs roughly $1 million per mile of coastline to evacuate, accounting for lost business, boarding up infrastructure, and the massive logistical strain.
If your cone of uncertainty is huge, you have to order hundreds of miles of extra coastline to evacuate just to be safe.
And worse, if you overwarn people who end up seeing sunny skies, they develop cry wolf fatigue and might ignore the next warning.
Exactly. By shrinking the cone with better data and better models, you only evacuate the people who are in direct peril.
NOAA provided the economic arithmetic on this in our sources. Between 2009 and 2022, improvements in hurricane forecasting alone generated an estimated $7 billion in avoided losses and targeted preparations.
$7 billion saved.
And the cost to achieve that specific improvement. The agency's hurricane forecasting budget over that same period was about $350 million.
That is a 20-to-1 return on investment.
If a private equity firm delivered a reliable 20-to-1 return, they would be legendary.
And looking at the broader picture, a nationwide survey found that the U.S. public consumes approximately 300 billion weather forecasts a year across all platforms.
That massive consumption generates an estimated $31.5 billion in household and economic benefits annually. The total public and private cost to run the entire infrastructure, the satellites, the planes, the labs, the supercomputers, is roughly $5.1 billion.
It is the ultimate invisible safety net.
But because it is largely invisible, we have a massive systematic accounting failure in how society views this science. Think of it like municipal plumbing.
That's a really good point.
You only ever think about the pipes when they break and flood your basement. Otherwise, they are quietly keeping your city functioning every single day. The government spreadsheet sees the $5.1 billion going out to maintain the laboratories and satellites.
But what the spreadsheet struggles to quantify is the value of a farmer in Iowa who checks a seasonal forecast, dynamically changes the type of seed they plant, and saves their family farm from ruin during a drought.
It doesn't accurately capture the value of a commercial airline routing a jetliner around a supercell, saving thousands of gallons in jet fuel, and preventing severe turbulence injuries.
In classical economics, weather forecasting is the textbook definition of a public good. It is non-excludable, meaning you cannot reasonably stop anyone from looking at the sky or hearing a forecast.
And it is non-rivalrous, meaning my consumption of a forecast does not diminish your ability to consume that same forecast.
Because it is a pure public good, private markets will never adequately fund the foundational science.
You cannot put a paywall on the NOAA radar that tells a rural town a tornado is 13 minutes away. It relies entirely on sustained, patient public investment.
And this brings us to the very sharp, sudden turn in our narrative. We reach the absolute peak of this scientific journey, and then we immediately hit a cliff.
The peak arrives on October 5, 2021. The Royal Swedish Academy of Sciences announces the Nobel Prize in Physics.
Half of the prize goes jointly to Klaus Hasselmann and Syukuro Manabe. Syukuro Manabe, now in his 90s and still working as a senior meteorologist at Princeton, received the highest honor in science for the mathematical foundation. He began coding on punch cards in the 1960s.
The Nobel Committee explicitly cited their work in the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming.
It is the ultimate vindication.
The researcher who started with a 1D vertical column of air is recognized for building the fundamental architecture of Earth system science.
The Geophysical Fluid Dynamics Laboratory, GFDL, releases statements honoring their scientist. It is a moment of total triumph for the entire infrastructure we've just detailed.
But the source dossier pulls us forward from 2021 into the present day. We are looking at the FY 2026 budget proposal from the Trump administration.
And looking at the FY 2026 budget proposal, the documents lay out specific, severe financial restructurings.
We want to be clear that we are simply reading the numbers and the official rationales provided by the Department of Commerce exactly as they appear in the dossier.
According to the proposal, NOAA's Office of Oceanic and Atmospheric Research, the division that houses the climate, weather, and ocean laboratories, faces a 74% budget cut.
The funding drops from roughly $600 million down to under $200 million.
The proposal goes further, detailing the elimination of funding for NOAA's climate, weather, and ocean laboratories and cooperative institutes.
That includes the Geophysical Fluid Dynamics Laboratory, GFDL. The specific laboratory where Manabe built the models that won the Nobel Prize is slated for closure under this budget, according to the documents.
The structural impact detailed in the dossier involves the termination of roughly 1,000 NOAA employees.
That includes 10 scientists at GFDL who are on probationary status. It also details the termination of $4 million in joint Princeton NOAA collaborative research funding.
The Department of Commerce provided an official justification for these terminations in the documents.
The termination letter stated that some GFDL research was deemed, and I am quoting the dossier directly here, misaligned with the administration's priorities.
The specified reason provided in the text is that the research promotes climate anxiety in America's youth.
The dossier also includes perspective from a former top NOAA administrator speaking to ProPublica about the operational impact of dismantling these labs.
They stated that this would return U.S. forecasting capability, quote, back to the technical and proficiency levels we had in the 1950s.
Which, we started this deep dive in 1958 with a lone researcher trying to pull meteorology out of the dark ages of paper maps.
And now a former administrator is looking at the closure of that exact same lab and stating that the capability will revert to the 1950s.
It exposes a profound, terrifying fragility. What exactly are we losing if a lab like GFDL closes? It's not just the physical computers, it's the institutional memory.
Institutional memory in atmospheric physics is incredibly complex. You have millions of lines of code, some of it still rooted in Fortran, that have been continuously updated, debugged, and refined by generations of scientists over 60 years.
You have a deeply specialized culture of researchers who understand the specific physical parameters of how clouds form over the ocean versus land, and how to represent that mathematically.
You cannot simply fire those scientists, put the code on a hard drive, and expect a new team to understand how to fix the model when the atmosphere throws something unprecedented at us.
Like the rapid intensification of hurricanes, which the dossier notes is still a massive unsolved forecasting problem driven by record-warm ocean temperatures.
When a Category 1 storm explodes into a Category 5 overnight, the models often struggle.
You need human physicists working in dedicated labs to rewrite the equations to understand that rapid thermodynamic transfer. The radar domes and the satellites alone cannot write new physics.
The physical infrastructure, the planes, the buoys, the radar, is only as robust as the human institutions that maintain it and interpret the data it gathers.
Let's summarize the sheer scale of the journey we've traced today. We watched Syukuro Manabe translate the physics of sunlight into equations on a 1960s mainframe, mathematically isolating the exact thermodynamic fingerprint of greenhouse gases.
We saw Edward Lorenz prove that a rounded decimal point can spawn a mathematical butterfly that destroys a forecast within 2 weeks.
We detailed how humanity responded by building an absolute marvel of engineering, a planetary nervous system of balloons touching space buoys anchored in the deep Pacific, and aircraft flying directly into the eyewalls of hurricanes, all to feed data into the descendants of Manabe's models.
It culminated in a Nobel Prize and an economic masterpiece that saves billions of dollars.
And we end on the stark, ink-on-paper reality of a 2026 budget proposal that seeks to close the doors on the very laboratory where that foundational science was born.
If we connect this to the bigger picture, it leaves us with a critical tension. Today, there is massive excitement about AI weather models.
These algorithms can process data and spit out a global forecast in seconds, using a fraction of the computing power of traditional physics models.
But we have to remember what those AI models actually are. They are trained entirely on decades of historical reanalysis data.
Data that was painstakingly gathered by the physical balloons, the deep ocean buoys, and the generations of scientists at labs like GFDL.
The AI algorithms don't actually know fluid dynamics. They don't understand the physics of a carbon molecule. They only know how to recognize patterns in the human-gathered historical data.
Which presents a chilling paradox for you to think about. The physical instruments might still fly for a while, and the AI algorithms will certainly continue to run.
But what happens when the institutional memory, the human beings who actually understand the underlying thermodynamics, who know how to anchor the models to physical reality, is scattered?
If the human architects of that physical reality are gone, Can the AI algorithms survive on their own when the climate inevitably enters a state it has never seen in its training data? We managed to clear the diagnostic muddy waters. We built a machine capable of seeing the future with astonishing clarity.
But now, just as the climate enters uncharted territory, we are looking at a proposal to systematically dismantle the human minds that built the machine in the first place.
Thank you for joining us on this deep dive into the architecture of the sky. We hope that tomorrow, when you check your phone for the forecast or just look up at the clouds, you see the massive invisible grid, the underlying physics, and the generations of rigorous human obsession that made it all possible.